Biology students. So we are going to continue talking about our patterns of inheritance. And in today's tutorial video, we are going to be talking about sex-linked traits. So when we say a sex-linked trait, we are referring to traits found on the sex chromosome. So we've previously talked about how the 23rd pair of chromosomes are referred to as the sex chromosomes. And if you are XX, that makes you a biological female, or if you are XY, that makes you a biological male. So how we're going to set up these Punnett squares is we are going to include the sex chromosomes in the Punnett square, but we're going to represent the trait, aka the allele, as like a little superscript you can kind of see as examples down below. So most of the Punnett squares we are going to be doing are considered to be X-linked traits, which just mean the trait is found on the X chromosome. So that's why you see that we've put the trait or the allele on the X chromosome, but it wouldn't be found on the Y. So when we set up the father and we look at the biological sons, that's why there's no little gene or allele represented on the Y chromosome. So if we were to go ahead and do a problem, here we have the trait hemophilia, and how the alleles would work is if you have the X chromosome with a capital H, that's going to be our dominant trait. Hemophilia is a recessive trait. So we would represent that X now with like a little h to still follow the patterns we've done before. So those with the capital H, aka the dominant trait, would have normal clotting blood. Those with the lowercase h would have the sex-linked trait hemophilia, which just means not normal blood clotting. So now if we were to go ahead and do the combination of genotypes, if we have two X's, each with the dominant trait, that's going to be a normal female. A normal female would also be somebody who is considered to be heterozygous, because remember, as long as you have one of those dominant alleles, you're going to express the dominant trait. So the only way a female would be able to possess the trait of hemophilia is if both of her X chromosomes each carried the recessive allele. Now, it's a little bit different for males because notice there's only two lines left. Males only have one X chromosome, so they actually have different genotypes than our females we just walked through. So if a male has just one capital H on his X chromosome, he would be a normal male. But again, notice we don't have anything on the Y chromosome there. We leave that blank because that trait isn't carried on the Y, only the X. So a male only needs one of his only X chromosome impacted in order to express the sex-linked trait. So we're going to take these genotypes, and just like we've set up past Punnett squares, we're going to have our parental cross, and kind of I'll show you how we fill it out as we go through. So we are going to take a man who has hemophilia from our prompt over here. So that means if we were to fill that into our cross, that's our option where just the one X chromosome is impacted. And then if we take a woman who is a carrier is just another way of saying heterozygous. So we see that there's only one option for females to be heterozygous. So that is what we would put on the second line. So if we transfer that down below, notice again, we have our sex chromosome set up and the alleles. So now when we go ahead and fill it out, same etiquette applies as before, is we're going to put that capital letter before the lowercase, but notice we have to include the sex chromosomes. So we see how this female sex chromosomes are in both. We just see this individual's heterozygous. This would be considered homozygous recessive. Then we go ahead and when we fill out the male boxes, etiquette is the X chromosome always goes first. We still include the Y to represent that that would be a son, even though that Y doesn't carry anything. So we'd see our two combinations from dragging those chromosomes into their respective boxes. So when we look at the probability, just like before, we kind of see the combos of what's in the boxes. So with our first option, we see there's only one out of the four boxes where it's a biological female who has a dominant and a recessive allele, so 25% chance of having that genotype. Same thing with this second genotype, only a 25% of having a female who's homozygous recessive. Then our third option of our 25% is going to be a male with the dominant trait and a 25% chance of having a male with the recessive trait. So when this codes into the phenotype, we have to include the biological sex, because now just saying the chance of having hemophilia or not is linked to a sex-linked trait. So we have to also include, okay, whether or not this is going to be a son or a daughter. So if we look at our first one, we have a 25% chance of having a daughter who is normal, a 25% chance of having a daughter with hemophilia, a 25% chance of having a son with normal clotting blood, and a 25% chance of having a son with hemophilia. So similar to what we've done with our Punnett squares in the past, again, really the only big difference is now just including the sex chromosomes in our cross and including whether or not they're going to have a daughter or a son. So let's go ahead and try another problem, but I would like you to pause the video and try and go through and solve this one on your own and then check your work. All right, now that you've gotten the chance to try the problem, we are going to go through and walk through it together. So we, in this case, have a man who has normal clotting blood. So there's only one genotype option for that. It's our male with the dominant allele. And then we're going to cross that male with a woman who has hemophilia. So in order for a woman to have hemophilia, remember both their X chromosomes have to have the recessive allele. So when we go ahead and set that up down below, we follow our etiquette of including our sex chromosomes, and the capital letter always goes in front of the lowercase letter. So we have our female boxes filled out there. When we go ahead and fill out our sons, those are our combinations from just dragging those chromosomes down and across. So now when we go ahead and look at our probabilities, this time we have a 50% chance of having a heterozygous female and a 50% chance of having a male with hemophilia. So we've written out the genotypes there. Those probabilities carry over to our phenotype, so we just have to include that 50% chance of having a daughter with normal clotting blood and a 50% chance of having a son with hemophilia. So that's writing it out. Sometimes some of these problems will ask, like, if you have a son, what is the chance of them having hemophilia? And in that case, we'd write 100%. We'll do some of those practice problems in class, but for now, this is just the general idea that you need to know about how to fill out a Punnett square when dealing with a sex-linked cross. So sex-linked traits can also be followed in a pedigree. So we've talked about autosomal recessive and autosomal dominant traits in the past. Now what we are looking at in this pedigree is a sex-linked recessive pedigree. So if we were to still just continue following the trait hemophilia, it would be similar to what we've done in the past, where if we label the generations, we have generation 1, 2, and 3. And if we were to number the individuals across, you just start from 1 on the left side and work your way over. So now when we determine the genotypes, we have to include their sex chromosomes. So I had mentioned this is a sex-linked recessive trait. So that means everybody who is shaded has the recessive genotype. So if we were to go ahead and look, we have 3 females who are shaded in. So if they are shaded in, they all have the sex-linked trait of hemophilia, meaning all 3 of their genotypes have to include 2 recessive alleles, 1 on each of those X chromosomes. So that's how we could identify what these females' genotypes are. Same thing with our males. There's only one option in order to be a male with hemophilia. So males with their XY chromosomes only need their X to include that recessive allele. So we can determine what these 5 individual genotypes are. And since we're dealing with a sex-linked trait, males only have 2 possible genotypes, whether they have the trait or whether they don't. So all of our males who are unshaded automatically have the dominant allele. So at this point, it's really just trying to determine, okay, what might these females be? So if we take a look at generation 2, at individual 2 and 4, we can see, okay, we know they're both females. So that means they have 2 X chromosomes and they're not shaded. So that means dad passed on this dominant allele, which is why none of them express the trait hemophilia, even though their mom had it. So mom passed on that recessive, but that dominant allele takes over. So both of these 2 individuals would be heterozygous. Now, if we look at generation 3, we see these two females, but in their combination, we don't actually know again if they are homozygous dominant or going to be heterozygous. So this is another case because females have more options when expressing the dominant trait of being homozygous dominant or heterozygous, unlike males in this situation. So they might possibly be either one. We don't have enough information to determine that. So kind of like how we've done in past pedigrees, where you've kind of had to write both to be like, can't assume, but these are the possible options. So this is a sex-linked pedigree. We're going to work on more examples of these in Punnett squares in class. If you are still a little confused, don't hesitate to go back and watch any of the problems again. But other than that, hopefully you are ready to try some problems on your own. Thanks so much for watching, guys.